as you said, I'm in the Department of Statistics. A lot of my research is focused on statistical analysis of geospatial data measured by satellite instruments. And so in that setting, we often apply Gaussian processes to large data sets. But recently, I've also started working on Gaussian process models in the context of machine learning. And today, I will give sort of an overview talk on these topics that combines several papers that I've co-authored with different students and collaborators. And those papers will be cited throughout the talk. So roughly speaking, here's an outline of my talk. I'm just going to give an introduction to Gaussian processes, and then I will talk about some of the basic properties of something called the Vecchia approximation. And then we'll see that we can apply the Vecchia approximations or extensions thereof in various different settings that involve Gaussian processes. And we'll see how far we get, but hopefully I can talk about all or at least most of them. Okay, so let's start with a very simple toy example. Let's say we're interested in estimating this function here that I've generated, but we've only observed it at certain input values, say at these black dots here. And maybe on top of that, the observations that we have are actually noisy, have noise or error in them. And so basically, we could imagine that we've observed these black dots and we want to infer this underlying gray function from those observations. And one way to do that is to use Gaussian processes, which you can think of as probabilistic function estimators. So basically, we assume something like an infinite dimensional normal distribution. So in some sense, a normal distribution for a function as a prior for the function from a Bayesian perspective. And then we condition on the data, we get a posterior, which is now, again, a distribution over functions that we can summarize in various ways. For example, if we just want in some sense sort of a point estimate of the function, we can get something like this red line here. But we really get a big sort of infinite dimensional joined posterior distribution that quantifies the uncertainty very naturally and can be, again, summarized in various ways. So, for example, we could compute point-wise prediction intervals like I've done here, but we could also answer questions like, what is the probability that the function anywhere in the input domain exceeds some threshold, for example? But many other questions of interest could be asked and can be answered based on this posterior that we get out once we condition our Gaussian process on the data. Here's what the solution would look like if the data don't have noise in them, and then obviously we get a much more precise estimate of what the function looks like, and our intervals become much narrower. And I'll come back to this case in a little bit as well. Okay, now this toy function that I used on the previous slides, what could that be in practice now for real applications? Well, it could be a time series. It could be a geospatial field, and as we've said, that's what in the context in which I've worked with Gaussian processes the most. We do things like kriging, which is essentially spatial prediction, or we can also use this Gaussian process as a surrogate for the output of a computer experiment and emulate that, or we can do nonlinear regression with the Gaussian process. And recently, we've also started working on using the Gaussian process as a surrogate for Bayesian optimization, black box optimization. So Gaussian processes have some nice properties that in principle make them well suited for various big data applications. So as we've already seen, we can gap fill noisy data with very natural uncertainty quantification. Another nice thing about Gaussian processes is that they are, from a Bayesian perspective, a non-parametric prior. And that means with the same kind of model, without having to change anything in the Gaussian process, any tuning parameters, anything, once we get more data, we naturally can sort of learn more and more about the function of interest. So here, when we have more data, for example, you can start learning that there's a little bump here in the function, in the true function of interest, which we would not be able to discern based on this small amount of data here. So this bump here, we cannot learn from small amount of data, but with the same Gaussian process model, as we get more data, we can learn even some very fine scale features in the function. Gaussian processes are also very flexible, so they depend on something called a covariance function or kernel function. And if we specify that appropriately, we can also sort of deal very well with settings where the function of interest has very different behavior in different parts of the input domain. So here, for example, is a toy function that is sort of very rough on the left and then much more smooth on the right. So we have some nice properties for Gaussian processes. The big drawback of Gaussian processes is that they are not scalable. So what does this mean? That means if we have n observations, n data points, we need to take this kernel function that I talked about earlier, this covariance function that I'm calling k here, and we have to essentially form an n by n covariance matrix by evaluating it at all pairs of input values. So these x1 up to xn, these are sort of the input values in a spatial context, the spatial locations at which we have observations. And we need to take all n squared pairs of them and evaluate the kernel function there and form this n by n covariance matrix. And working with this, well, first of all, just computing that matrix, but also then working with the matrix and say decomposing it is very, very expensive if n is large. So roughly speaking, this will then scale cubically in time and square in terms of the memory complexity. So what that means in practice is if we have a data set with a couple of thousand observations, we can apply Gaussian processes, no problem. We can do inference very quickly. But then the computational cost increases very quickly as we go to larger data sets. Even with 100,000 data points, it's almost impossible, at least on a regular workstation, to really just do direct inference using a Gaussian process without any simplifying assumptions or additional sort of tricks. And so this cubic complexity there is really hurting us when we get to larger n. And so what we want in this talk, basically, we want methods or approximations that scale roughly linearly in n. And as we'll see later, also on top of that, we will have our methods are very parallelizable. And we can even do some things like mini batch subsampling to speed things up even more. But roughly speaking, we want to get from this cubic to linear complexity in n. Now, Gaussian processes have been around for a long time. You know, this problem of working with large covariance matrices, that's a computational issue, has been recognized for a long, long time. And so there are literally many, many thousands, probably tens of thousands of papers out there that try to deal with some aspect of this computational issue. And I've just, you know, listed a couple references here, but this is by no means exhaustive. So existing approaches include those that either directly apply or assume that the covariance matrix is of low rank or low rank plus diagonal. Then there's a lot of approaches that essentially impose sparsity, so lots of zero values in the covariance matrix. And then I'd say more recently, people have also been more interested now in assuming sparsity in the precision matrix, so the inverse of the covariance matrix, assuming that that matrix has a lot of zeros. And the approximation that we'll talk about today, which was originally or stems from an idea from Vecchia in 1988, essentially implies a sparse Cholesky factor of the precision matrix. And this is really what gives us the linear scaling that these other methods here cannot really give us in general. But this here, if we sort of directly apply or assume that the Cholesky factor of the precision matrix is sparse, that's what gives us that linear scaling in it. Okay, so let's talk about this Vecchia approximation in a little bit of detail, but again, it will be at a fairly high level and more of an overview. So a little bit of notation here, sorry. We're gonna assume that we have a vector y equal yl1 up to yn. So these could be simply n observations, realizations of a Gaussian process. And so if we assume a Gaussian process, then the joint distribution of this vector will be a normal distribution. For simplicity here, we'll assume it has mean 0. And then this covariance matrix sigma that we talked about earlier. So this is an n-variate Gaussian distribution. Now, any joint density can be decomposed in this way here. So if we look at the probability density function of y, you can write this as a product I equal 1 up to n, where we consider univariate conditional densities of yi given everything that was before. So essentially, yi will condition on y1 up to yi minus 1. Sorry, there's a bit of construction out there. I cannot hear too much of that on the call. Once we have this conditional density here, or these conditional densities, you know, that by itself doesn't really give us any computational advantage, but it motivated this approximation by Vecchia in 1988. And he said, instead of looking at this P of y, let's look at a P hat of y, an approximation thereof, which is also a product of univariate conditional densities. But now, instead of yi conditioning on everything that comes before, the entire history, we just condition on some small subset thereof. So say y10, instead of conditioning on y1 up to y9, let's assume it only conditions on for example, y7 and y9, maybe only 2 points, for example. And so this qi here is what we call the conditioning set, or more precisely, the conditioning index set. And we're going to assume that all of these index sets are at most of some size m. So for I equal 1 up to n, all the conditioning sets are at most of size m. And so this m now becomes sort of a tuning parameter. Basically, if we make m larger and larger, we're going to get more and more accurate approximations. So this p hat will become closer and closer to p. But we're also sort of having more and more expensive computations as we increase m. The sort of important thing here is that in many applications, though, in many settings, we can actually get very high accuracy. P hat can be very close to p, even with a very small m. And this is due to something that in spatial statistics, at least, is often referred to as the screening effect. And so we'll see some of these settings in a little bit. But basically, in many settings with a pretty small m, we can get very accurate approximations. And since the m is small, we actually also get low computational cost. So the two things we have to sort of, figure out or decide on if we want to apply a Vecchia approximation to a Gaussian process are how do we order y1 up to yn? So up here, the ordering doesn't matter. This is always an exact representation. But for this here, the ordering can very much matter. And then given the ordering, we have to choose these conditioning sets, these QIs. We have to sort of say which of the past things do we actually condition on. And so this slide is sort of roughly about that. Traditionally, what people did when they applied Vecchia approximations was to use a coordinate ordering. So here we have essentially 100 n equal to 100 observations here, or locations at which we have observed a y. And so we have 10 by 10 input grid here in 2 dimensions, 2 input dimensions. And here in red, I've colored sort of the, I think it's the 56th point in the ordering, the 56th location in red. And now in green are all the points that are ordered previously. So those are basically y1 up to yi minus 1 if we use coordinate ordering. It turns out that it can be much more accurate for Vecchia approximations if we use something called a maximum minimum distance ordering, which I won't go into details here, but this is sort of an illustration of what that might look like in the same setting, but just now using this maximum ordering. And then once we've decided on the ordering, then we have to decide how to choose these conditioning sets, these QIs, as a subset of the green points of the history. And so what we typically do there is we simply condition on the m nearest previously ordered neighbors. So here, for example, these are the m equal to 8 in blue, nearest previously ordered neighbors to this red point. And similarly here in blue, we have the m equal to 8 nearest previously ordered neighbors to this red point. And so for this talk, we're typically going to be sort of, when we talk about Vecchia approximation, we're going to talk about a Vecchia approximation under maximum ordering with m nearest neighbors as our conditioning set, nearest neighbor conditioning. And that's what we found sort of works the best in general, although there will be sort of slight variations of that depending on the setting. Okay, so what we've seen here is, this this decomposition here of this density is equivalent to this joint distribution here, where we have this covariance matrix sigma. It turns out that this Vecchia approximation, so this p hat here, this product of conditional distributions, also corresponds to a joint normal distribution, but it corresponds to a normal distribution, of course, with a slightly different covariance matrix that I'll call sigma hat here. So ideally, this sigma hat will be close to sigma, but it generally won't be exactly the same. So there's sort of a new covariance matrix here, an approximate covariance matrix. And one important thing that we're going to focus on is what I'll call the inverse Cholesky factor, or equivalently the Cholesky factor of the precision matrix of sigma hat inverse. And it turns out that if we assume this Vecchia approximation here, and we're given our kernel K, or we can access elements of this covariance matrix sigma very easily, individual elements, then we can compute the non-zero entries of this inverse Cholesky factor very, very easily and in closed form. So it's sort of easy to get this representation here, given this assumption. Now, we have a recent paper where we've studied the Vecchia approximation more from a matrix approximation perspective. And so it has a very nice interpretation from that perspective as well. Specifically, let's assume we want to approximate our covariance matrix sigma. by some other covariance matrix. And we're going to assume that this covariance matrix that we use to approximate sigma has a sparse inverse Cholesky factor. So we're restricting ourselves to the sparsity set S here, which is essentially determined by these QIs. So we choose the QIs beforehand, these conditioning sets, which essentially now correspond to non-zero entries in different columns of this U matrix. And so the diagonal will be non-zero and the entries that correspond to these QIs. And we're restricting ourselves to this sparsity set here. And now we try to solve this optimization problem, namely we want to find the U hat in the sparsity set that minimizes the KL divergence between the exact distribution, so this normal distribution with mean zero and covariance matrix sigma, and a normal distribution that is implied by this U or U hat here. Okay, and so this looks like a very, very complicated non-convex optimization problem. But it turns out that the U from our Vecchia approximation is actually the optimal sparse triangular matrix that solves this optimization problem. And so sort of by definition here, if we look at this problem like this, we're obviously going to have a sparse matrix U. And specifically, since the non-zero entries here are determined by the QIs, there's at most M off-diagonal non-zeros per column. So we can sort of directly, by choosing M, to control how many non-zeros there are in this sparse Cholesky factor. We can also compute this solution here in closed form in order nm cubed time. So instead of cubic in n, it's now essentially becoming cubic in m, where again, the m can often be very, very small in many, many settings. And on top of that, turns out when we're solving this problem here, the computations for each of the n columns are actually embarrassingly parallel. So there's sort of, the computations I do for the 10th column have nothing to do with the computations I do for the 11th column. And so, in some sense, the complexity is even lower if we have lots of computational cores where we can distribute our computational task. So different way of looking at the Vecchia approximation, but sort of also a very nice approximation interpretation from that perspective. Okay, let's sort of look a little bit at, does this Vecchia approximation actually work well? And here's just a little bit of evidence that at least in certain settings, it works extremely well. So here's our toy example again in the setting where we have no noise. The noise is zero. We're directly observing the function at certain input values. So this was the exact solution. This is basically what we want, but it's too expensive if we have large n. And here is the solution that we get with Vecchia overlaid in blue. And so this is a solution that we can compute very, very quickly, even when n is very, very, very large. And we can see here even with m equal to 4, very small m, we're basically getting the exact same solution, except for maybe a couple places where there's a slight discrepancy, but we are getting essentially the same thing as with the exact Gaussian process. So in this particular simple example, at least, we're getting a very good approximation with a small m. We can also do a little bit of theory on this, actually. So if we, for example, consider Matern type covariances, exponential covariance would be a special case of that, for example, under what we often call infill asymptotics in spatial statistics. Won't go into the details of that here. Using our maximum ordering that we set, nearest neighbor conditioning, and some regularity conditions, if we're in d input dimensions, it turns out that an epsilon accurate approximation can be computed in order n log to the power 2d n over epsilon time. And so this is actually sort of the best known complexity that you can get for the problems that I've sort of hidden here a little bit with regularity conditions with details in the paper. The best known complexity that we're aware of for this setting for this class of problems. What this also implies here, this asymptotic result, is that we can essentially get consistent estimation and prediction and consistent inference when m only grows sort of polylogarithmically in n for fixed d. So it can especially for small d, for small input dimension, m can grow very, very slowly with n, and we still get sort of essentially the same asymptotically the same inference as we did with the exact Gaussian process in this setting. Another interesting thing about the Vecchia approximation is that we can actually view a lot of existing Gaussian process approximations, and this will only be interesting to people who are familiar with some of them. We can actually view a lot of them as special cases of this Vecchia framework. Basically, by choosing different orderings and different conditioning schemes, we can get different existing approximations. For example, several of these low-rank approximations that I talked about earlier, like FIC or modified predictive process, they're special cases. The PIC that maybe some of the machine learning people in the audience will have heard of is also a special case, multi-resolution approximation, nearest neighbor Gaussian process. So all of these are basically just different versions of Vecchia approximations if you view it in the right way. What we haven't really talked about yet is in Gaussian process inference, we usually want to make prediction at unobserved locations or input values. And what we would do in that setting is we simply apply the Vecchia approximation, not just to the vector of data, y1 up to yn, but we simply append at the end of this vector also the Gaussian process at locations or input values at which we want to make predictions. And then we have sort of a big joint vector and we apply Vecchia to that. And I'll just, for the purpose of this talk, leave it at that level of detail. Okay, so this was sort of roughly speaking some nice properties and what the Vecchia approximation looks like. Now let's talk about this Vecchia approximation in different special or specific settings. Maybe most importantly, for Gaussian process inference, the setting when we have Gaussian process plus Gaussian noise. So this is often the assumption when we apply Gaussian processes, including in spatial statistics. Often the assumption is what we're observing is a Gaussian process with some smooth covariance function or kernel, like on a turn, plus some independent Gaussian noise. So now basically our covariance matrix sigma is sort of a kernel matrix corresponding to some smooth kernel, say on a turn, plus a diagonal matrix that corresponds to this independent Gaussian noise. Well, what we can do now is we can apply our standard Vecchia approximation directly to the data. So from a matrix approximation perspective, directly to sigma here. If we do this again is the exact GP, and this is our Vecchia approximation. Now, assuming that the diagonal term is 0 without noise. And here's what happens when we apply it in the setting where the diagonal term is non-zero, so we have noise. And what you can see now in red was our exact GP solution that we saw at the beginning of the talk. That's what we would want. In blue is the approximation that we get with Vecchia with m equal to 4. And now we can see those don't agree at all. So this is a horrible approximation, huge approximation error. We don't want this. But it turns out that we can actually salvage this very easily, or in some sense very easily, at least conceptually very easily. Namely, we can simply apply what we call latent Vecchia, which we apply to the latent GP. So in other words, we apply to the K. So in some sense, we are first approximating the K, the smooth sort of kernel matrix, and then we're adding that diagonal term later, conceptually speaking. And what you can see now, even with m equal to 4 again, we're getting essentially an exact approximation. So the approximation error is becoming essentially 0. Again, conceptually, this is very, very simple. One big problem with this is that when we do this latent Vecchia, we actually also have to decompose the posterior precision matrix and compute its Cholesky factor. And it turns out, because there can be a lot of fill-in, that this Cholesky factor can be quite dense and therefore expensive to compute. So in other words, this latent Vecchia is ultimately actually a lot more can be a lot more expensive than the standard Vecchia, where we just apply to sigma. But it turns out that there's a second approximation we can do and simply compute this Cholesky factor of the posterior precision using something called an incomplete Cholesky algorithm. And if we do that, we can sort of get back to the cost of, roughly speaking, of the original Vecchia, but get a much better approximation when we have Gaussian noise. So what these plots here show is basically the log KL divergence. So lower is better here. For varying noise levels, small noise to large noise, and different m's. So this is essentially sort of a small m versus a large m, where we have higher accuracy. And what you can see, what we call here naive in this figure, that's just the standard Vecchia. So this is cheap, but very bad approximation. What we would really want is this exact latent Vecchia in gray. This is much more accurate. But again, this is potentially very, very expensive. But if we apply this additional incomplete Cholesky approximation, we get this red line. And so we get a very cheap approximation that's almost exactly the same as the gray line. So it's almost as good. And there's basically almost no additional error due to this incomplete Cholesky factorization. And so that's what we propose to do in this setting where we have a Gaussian process observed with Gaussian noise. Okay. We can also apply Vecchia in the setting of a generalized Gaussian process. So this is now basically using a Gaussian process at a latent level to model non-Gaussian data. So conditional on the GP, the data could be from any exponential family distribution. Could be, we could look at binary data for classification, categorical data, counts, right-skewed data using a gamma distribution, for example. And so this is sort of a class of GPs then that are sometimes referred to as a generalized GP. I have an example here based on, or that deals with binary classification, so where our data is sort of 0-1 type data, and then we could use a logistic generalized Gaussian process to model that. I think in the interest of time, I'm gonna just sort of skip over that a little bit and just say, if we use something called a Laplace approximation, many are probably familiar with that, the Gaussian approximation, then it turns out that the inference that we have to do is essentially just an iterative version of the inference in the previous subsection. So where we have sort of Gaussian process plus Gaussian noise. And once we're back in that setting, we can use the same techniques as in that previous subsection. We just have to do it iteratively now because there's essentially a Newton-Raphson type optimization procedure as part of this approximation that we have to go through. And so we basically do the same thing as in the previous subsection, but sort of multiple times. And I'll just leave it roughly at that for the purpose of this talk. Just here, this very briefly, this works very, very well. This is the Vecchia Laplace approximation relative to, say, a low-rank approximation of the Gaussian process using that same Laplace approximation on top of it. Let me talk instead a little bit more detail about some more recent work that we've done where we've tried to apply Vecchia for computer model emulation. So the setting here is that we have some very expensive computer model that maybe has to even be run on a sort of a high-performance computing environment. And so we have, we're interested in some function essentially as an output for different input values. And we want to emulate this function, this computer model output, using a Gaussian process as a surrogate model. But now if we have a lot of evaluations of the function, if it's in somewhat high dimensions or we want to get fairly precisely, we want to know what that function is, we need a lot of function evaluations, and we essentially are back in that large N setting. So we have a Gaussian process with large N. It's just now a Gaussian process that is a function of various different input values to this computer model. So the inputs now are the inputs to this computer model. They're not like spatial locations like what I would usually think of coming from a geospatial background. And what do we do in this setting? Well, now sort of the input space, the different input dimensions can be sort of quite different things, right? One might correspond to the weight of an airplane, and the other one, say, the length of the wing of the airplane. And then the output is somehow like, how much gas or fuel you need per hour of the airplane flying, something like that. So anyway, the inputs now can be very, very different things. So what people would typically do there is to just sort of standardize them to 0, 1, say. So here we have 2 input values, both standardized to 0, 1. And then, you can apply your Vecchia approximation in that setting. So we do a maximum ordering. We condition on the nearest neighbors. Here, m equal to 4 nearest neighbors for the 28th input value. And apply Vecchia in this sense. But what we typically do then in this setting actually is that we use something called an automatic relevance determination kernel. And this simply means that each input dimension has a different range parameter or length scale parameter, or the inverse of that we just call the relevance. So the relevance is sort of the inverse range. So each input dimension here will typically now have a different relevance, a different range parameter. And what we do, or what we proposed in this paper here, is that we actually apply our Vecchia approximation, or more specifically the maximum ordering and the nearest neighbor conditioning, in the scaled input space, in which each input is sort of multiplied by its relevance. So if we go to the scaled input space and we look at the sort of Vecchia that was applied in this 0, 1 unit square, unit hypercube domain, and we look at this in the scaled input space, in which distances are actually really relevant, or make sense. It turns out that this is actually not a very good approach to do, this red approach here. And so, you can see this here, the 28th input value should really condition on the 26th and 27th, because they're very, very close in this scaled space. But instead, it's conditioning on 9 and 23. And that's going to lead to a very bad approximation. And so what we do instead, we directly apply Vecchia in the scaled input space, and we get this black solution here, or this black maximum ordering and nearest neighbor conditioning. where now the 28th input is sort of conditioning on what is really the nearest neighbors. So, long story short, all we're doing is we're applying Vecchia in this scaled space where each input dimension is scaled by its relevance or by the inverse of its range parameter. If we don't know the range parameter, which is typically, of course, the case, so we learn it iteratively and we update this scaling as we go through an iterative parameter estimation procedure based on Fisher scoring. And so this is just sort of a very brief look at how well this can work. So on the on the y-axis, we essentially have again KL divergence on a log scale, and here we have m on the x-axis. So as we increase m in the size of the conditioning sets, we get better and better approximations. And what we can see here is that the KL divergence for this scaled Vecchia approach is much lower than for this Vecchia approach. Sorry, here that applies Vecchia in the space on the unit hypercube, the input space, and it's also even more accurate than, say, a low rank type approximation, which are very popular in this setting, but also more generally in machine learning for Gaussian processes. And in fact, it turns out like even with m equal to, I don't know, this was I think m equal to 5, we're getting a better approximation with S Vecchia than with Vecchia with m equal to 50. And due to this cubic scaling in m, this is essentially like 3 orders of magnitude improvement or more. And so this is here with known parameters. Here's the result that we would get when we do this iterative estimation at the end. Essentially the same results. This is here in 10 input dimensions. Here's sort of a brief overview of some results that we got for sort of a real application where we looked at a real satellite drag computer model. So this is a computer model that models the drag that you get on a satellite orbiting Earth as a function of various different characteristics of the satellite. And so there's an existing analysis of this sort of computer model output and GP emulation results in this paper here. And we basically compared to their results and their methods. So in blue here, you have various different versions of their methods. So they basically have sort of all kinds of variants of very similar types of methods. And the RMSPE that you get on a sort of a test set if you do make predictions on a log scale here again. And then importantly here, the circles are the scaled Vecchia. You can see that scaled Vecchia outperforms all these, I don't know how many there are, but maybe on the order of 20, 30 approaches in the Sun et al. Paper. And on top of that, it's doing it in a computation time that's 2 orders of magnitude faster than these light blue methods here, for example. So it's much, much faster and more accurate. What else should I say? Okay, so this example here, for example, we had n equal to 2 million, and there's these 6 different chemical species. So that's not so important, but basically sort of 6 different settings. And here we had 8 input dimensions for this satellite drag computer model. Okay, now some very recent work that's actually still in progress, in preparation. Now we want to do Gaussian process regression and variable selection using these Vecchia type approximations. And so what we're going to focus on is sort of a setting where we have a large n, as before, but also a potentially very large d. Say we have a regression setting with 1,000 or even a couple thousand or even 10,000, say, covariates or predictors, potential predictors. And we're going to do, again, a Gaussian process regression with an ARD kernel. So a similar setting as before as in the computer model setting, where each input or dimension or each predictor or each covariate has its own range parameter, or the inverse of that, again, we call the relevance of that input. But now we're also interested in the additional feature, which is variable selection. So we're going to say maybe we have 1,000 potential predictors, but maybe only some of them are actually truly relevant. Maybe only some of them affect the Y, the response. And so we basically want to essentially identify and remove covariates that have 0 relevance. So we call this relevance parameter for the Lth input or the Lth covariate RL. And if that is equal to 0, then that means that particular predictor doesn't have any effect on the response. And so what we basically want to do is we want to estimate R1 up to RD, these relevances for these D potential predictors, plus another couple of parameters that I won't go into details for, and we call that vector theta. So that's what we want to estimate. And we propose to do this by optimizing a penalized version of the Vecchia log likelihood. So we have here our p hat of y that I talked about, toward the beginning of the talk. So this is simply our Vecchia approximation to the joint density of y. Now I've put a theta here in the subscript because this, of course, does depend on what the relevances are. Essentially, what the relevance is determined at the kernel, and then the kernel determines this, density here. We take the log of that, the negative log, and then we're adding lambda times some penalty term for theta. And I won't go into the details here of what this penalty is, but it's basically sort of penalizing RLs that are non-zero and that are potentially large. And it's penalizing it more the larger lambda is. And so we have an algorithm that we call CQCD, which essentially iteratively minimizes a quadratic approximation of this objective function using constrained coordinate descent. If none of these things mean anything to you, then don't worry about it. But basically, we're trying to sort of find the minimum of this function here using this algorithm. And the important thing is, within these algorithms, we iteratively need a quadratic approximation of h. And it turns out that we can get this very, very nicely using Vecchia. We need sort of an approximation to the first and the second derivative of it with respect to this theta vector. And we can get this very nicely, the gradient and the Fisher info, which gives us sort of a second order derivative for this Vecchia using an approach that was proposed by Guinness in 2021 that sort of works very, very well and is very, very fast and sort of jives perfectly with Vecchia. Here's an example of what the CQCD algorithm does sort of over a number of iterations. From some starting point here, we have d equal to 100 covariates. So we have R1 up to R100 on the y-axis on a pseudo log scale. And we have, what we're assuming here is that 5 of those 100 covariates are true covariates that actually affect the response, and 95 are fake. And so the fake ones here are in gray, and we can see after, I think, 3 iterations here of the CQCD algorithm for a fixed lambda, the fake predictors are deselected or removed from the model. They're all exactly 0 relevance here. And the true predictors, which are in different colors here, converge fairly quickly to their sort of roughly what their true values are. So the dashed lines here are what the true values were from which we simulated the data. And so the CQCD algorithm here worked very well for this example for a fixed lambda. The question now, of course, becomes, how do we select lambda, or what do we do with the lambda? It's not something that's known. How strongly should we penalize the problem? And so what people do in statistics then usually is that they create a solution path where we start with a very large lambda. So we have very strong penalization and get a very sparse model. That's what we have on the right here of this plot. And then we sort of iteratively or sort of, bit by bit decrease the lambda until we get to, well, essentially lambda equal to 0, and where we have a much, much less sparse model. And now for each lambda value, as we go from large to small sequentially, we run the CQCD algorithm from the previous slide using warm starts. So when we have a good solution from the previous lambda, now we go to the next smaller lambda, we use the previous solution as our starting point for the next one. And very importantly, to keep the computation time small here when we have a very large D, very large number of potential predictors, is that we only add these covariates in small groups to a candidate set, and we only run CQCD on this candidate set based on the gradient of this objective function with respect to the square of the relevance. And we have some theoretical results that say that this is actually a very good way of doing this. So we compute the gradient, we select the largest ones, add those to the candidate set, run CQCD, and we sort of do this a number of times. And then we basically keep decreasing lambda, going from right to left in this plot here, as long as the out-of-sample predictions are improving. So that's sort of our stopping criterion. Once they stop improving, we stop. And for this particular example, that stopping point would have been this vertical red dashed line here. So this is exactly a point at which the true predictors are sort of close to their true values, and the fake predictors, none of them are selected. If we went to smaller lambdas, we would start getting some fake predictors in there with non-zero relevance, which we don't want. So this is the solution path here, just one toy example again, where we have d equal to 1,000 covariates, out of which 5 are true, and 995 are fake. And so, this is pretty high dimensional setting for a Gaussian process. Okay, what else? Oh, okay, yeah, and one other thing that is very nice with Vecchia, actually, I haven't talked about this here in any detail, but it turns out that mini-batch subsampling, which is very popular for IID data, actually also works extremely well in conjunction with Vecchia. You know, now we have, of course, dependent data. We have a Gaussian process, so there's dependence between different Ys, different responses. So we don't have IID data, but we can still apply mini-batch subsampling very, very nicely in conjunction with Vecchia. So that would lead to even further speed ups where, you know, we don't even have linear scaling in N, but, you know, linear scaling in whatever the batch size is. Okay, because I have a little bit of time. I'm not going to go into details here, but I just wanted to sort of say, you know, this Vecchia can be applied even more broadly to even more things that I don't have time today to go into. But you know, we've started working on Bayesian optimization using Vecchia. We can also apply it to sort of settings like multivariate Gaussian processes or space-time processes using something that we call correlation-based Vecchia. And there's also, you know, we've done quite a bit of work now recently on essentially extending this to a non-parametric setting in terms of the covariance structure. So what I've assumed so far throughout this talk is that the kernel, the covariance function is known up to some parameters. So for example, you know, here in this previous setting, there were lots of unknown parameters, but you know, there's still a finite number of parameters, and roughly here, order D unknown parameters. But we sort of assume that we have this ARD kernel, which of course is potentially a strong assumption. It might not be true in real life. And so what we started working on is also using ideas similar to Vecchia to make non-parametric inference on the covariance matrix itself, sort of on the covariance structure on the kernel function. Yeah, I won't go into details of this here, but I think next week I'm giving a talk in the Department of Biological and Agricultural Engineering where I'll talk a little bit more about this non-parametric inference. Okay, so let me wrap up here. So I've introduced this Vecchia framework for Gaussian process approximations. We've seen that at least in some settings, it can be highly accurate, and it can lead to an almost universal Gaussian process toolbox. You know, we can do sort of Gaussian processes without noise, with Gaussian noise, with, you know, we have non-Gaussian data for computer model emulation, for Gaussian process regression. And as I mentioned also, you know, in principle, we can apply this also in even more, you know, complicated or different settings. And so, you know, this Vecchia approach is sort of very versatile in that sense. And we can guarantee linear scalability in N, plus on top of that, for almost all the things I talked about, or maybe even all of them, we have these very nicely, embarrassingly parallel computations. And we can also use mini batching, as I said, very nicely in conjunction with Vecchia. We have some packages in the statistical software R that are on CRAN, which is their package repository. And then I wanted to acknowledge some funding here, including from TAMIDS, which is paying for half of a postdoc who's worked on this stuff here with me, Jen Cow, doing great work there. Yeah, so here's some references. I've tried to sort of annotate them a little bit. So this paper is sort of on general Vecchia. Here's Vecchia prediction. This paper is about this sort of Kullback-Leibler, Cholesky matrix approximation view of Vecchia. Here's this Vecchia plus Laplace for the non-Gaussian setting, scaled Vecchia, and then these non-parametric things that I didn't really talk about in detail here, but some references where you can read more if you're interested. That's it from me. Happy to